Hello and welcome to probably one of the most exciting lessons on the unit of vectors, the dot product. Remember that so far we have looked at geometric vectors, which are any two vectors placed on a plane. And then we looked at algebraic vectors, which are vectors placed on the Cartesian plane. We've learned how to add two or more vectors by using the triangle or parallelogram law, and subtract two or more vectors also by using the triangle or parallelogram law. And we've also learned how to multiply a vector by a scalar. In this lesson, we would learn how to multiply two vectors together. There are two different ways of multiplying two vectors, and our focus today will be on a form of multiplication that is called the dot product. This is the formula for the dot product. So on the left side, you see here vector u and v. These are the vectors we're multiplying, connected to each other by this dot, which represents the multiplication, and we read it the exact same way. We say u dot v. And on the right side, you see the magnitude of u, magnitude of v, and cosine theta multiplying each other. As you can see, magnitude of u will be a number, a positive number. Magnitude of v is another positive number, and cos theta will be a number as well. So the product of three numbers will give a number or a scalar. And this is the reason why very often we refer to the dot product as the scalar product. Now, as you can see in here, the dot product will relate the multiplication of two vectors in vector form with the multiplication of the magnitudes of two vectors and the angle between them. Remember that when we discuss geometric vectors, we only dealt or worked with their magnitudes and the angles that they would make respectively with one another. So this is the reason why we call the u, magnitude of u, magnitude of v, cosine theta, the geometric part of the dot product. And the other side, where you see the multiplication of a vector with another, is what we call the algebraic part. So we use the vectors in algebraic form for the left side and the vectors in geometric form for the right side. Now, it is very straightforward how we find the dot product of vectors in geometric form, or geometric vectors for short. And now we'll take a look at how to multiply two algebraic vectors. Remember that if you have two vectors, for example, in our case, u and v with coordinates x, u, y, u, and some vector v with coordinates x of v, y of v, we'll say that the dot product would be the product of their x coordinates plus the product of their y coordinates. So you find basically the sum of the product of the coordinates, and that gives the dot product of two algebraic vectors. And similarly, when we have a vector in 3D, we'll have a third coordinate, and the dot product of two vectors in 3D will be exactly the same like in 2D, but obviously we'll have to add the product of the z coordinates of each vector. Now, why do we study the dot product and how useful it is? So to start with, the dot product is probably at the foundations of many ancient and old mathematical formulas and geometry theorems. But for now, we are going to look at some applications of it to find the angle made between two vectors. And we're going to say that the dot product can be used efficiently to find the angle between two vectors. And for this, we find the cosine of the angle between them and use this very same formula you just solved for cosine theta, which means you isolate by dividing by magnitude of u and magnitude of v both sides. So as you can see in here, the cos theta would be u dot v divided by magnitude of u, magnitude of v, which in other words is the algebraic dot product divided by this part of the geometric dot product without the cosine. Now, what are the possible values of dot product? We said that it's a number, but could it be could it be any number, or does it have to be a specific number? When we think about it, remember that dot product is magnitude of a vector multiplied by the magnitude of another vector and the cosine of the angle between them. So we're basically multiplying a positive with a positive number, so these two will give a positive, and the sign of the dot product seems to be dependent only on the sign of cos theta. If the angle made between two vectors is acute, the cosine theta will be a positive number, which means that the product will be positive, 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 dot product will be positive. If the angle made between the two vectors is 90 degrees, the cosine will be 0. So we'll say that if cosine equals 0, then the dot product obviously will have to be 0. So the dot product is 0 again for a 90-degree angle. And if the angle made between two vectors is between 90 and 180, the dot product is negative, and that is because the cosine of theta, when theta is bigger than 90, will be a negative number. Now that we know the dot product formula and somehow where it comes from, we're going to take a look at the dot product live exercise to see how the dot product of two vectors changes as we change the parameter. So what you're seeing here is two vectors u and v. They make an angle alpha. It indicates here 81.3 degrees. And we have the dot product here on the left side. We have all the information about the vectors. And the dot product is represented by b equals u dot v. As you can see, the number below b here is 2.8, which indicates that u dot v has a value of 2.8. So I'm going to make this angle equal to 90 degrees and see what happens to the value of b, which is basically u dot v. Okay, so this will take a little bit of, all right, so it needs a good eye. All righty then. Okay, so it has to happen. So I'm going to make it about 90, and you can tell here that the dot product here indicates that it will equal 0. And if we make this angle bigger than 90, you can tell that the dot product is negative 7.2. And obviously, in a similar way, if the magnitude of each vector changes, keep an eye on the value of b on the left side of the screen, you can see that the value of dot product, which is represented by b, will change as well. So now let's take a look at a couple of examples where we can practice the dot product. So in the first example, we are given two vectors, a and b. They're sitting nicely and quietly here. And the magnitude of a is 12, magnitude of b is 16. The angle made between them is 60 degrees. So we have to find the dot product of these two geometric vectors. You see, they're geometric, they're not on the Cartesian plane, right? So we'll say that's magnitude of A, magnitude of B, and then cosine of 60. So substitute A, which is 12, and B, which is 16, and cos 60, which is 1/2, and then we get the value of 96 units. So we'll say that the dot product of these two geometric vectors will be 96 units. Sorry, we call them A and B. There we go. Problem fixed. Now, in the next example, we are given two vectors, and we will find both the algebraic dot product and geometric dot product. And I will start off with algebraic dot product because we haven't tried that yet. So if we are finding u dot v, means that we are multiplying 35.68. So which means that we're multiplying again, the x is together, the y is together, and adding them. So we have 3 times 6 plus 5 times 8. So 3 times 6 is 18, and 5 times 8 obviously 40. So we got that the dot product here is 58 units. So I'll write this down, and I will actually box it, because we are about now to find the dot product by using or treating u and v as geometric vectors. or as a geometric dot product. Remember, geometric dot product equals magnitude of u, magnitude of v, cosine of the angle between u and v, which for now we'll call it theta. So this means that we need to know the value of u, the value of v, and cosine theta, which we don't know yet. So we know that the coordinates of vector u are 3 and 5. So we'll say that magnitude of u must be square root of 3 squared plus 5 squared. So that will make it 9 plus 25, or square root of 34. Now, next we have to find the magnitude of vector v, which is the square root of vector v is 6, 8, 6 squared plus 8 squared. That would be the square root of 100, which is equal to 10. Now the question becomes, how do I find the angle theta? So for the angle theta, we have to be a little bit more creative. And to make things more clear, what I'm going to do is draw the two vectors, 3, 5 and 6, 8. So here we go. All right. I am going to scale this. Again, a lot of it will be estimation in my scale. And what we have in here is vector u, 3 and 5. So here goes 3 and 5. 1, 2, 3. And 1, 2, 3, 4, 5. And I will draw vector u first. Next, we'll draw vector v, which has coordinates 6 and 8. So 4, 5, 6, and here 6, 7, 8. And let's draw vector v. So the angle made between vectors u and v is this tiny little angle, right? And we called it theta. So I'll call this theta. In order to find angle theta, let me magnify this a bit. So in order to find the angle theta, we're going to need to know the angle that vector u makes with the positive x-axis. So in other words, we're going to need to know this angle, which for now we'll call it alpha. And we'll also need to know the angle that vector v makes with the x-axis, the positive x-axis, which for now we'll call it beta. So as you can see here, angle theta would equal angle alpha, take away beta. So we have the vectors given on the Cartesian plane, algebraic vectors. We can easily find alpha and beta. So we'll say that alpha equals inverse tan of y over x. So we're using the coordinates of the vector, which are 5 and 3. Use the calculator to find alpha, and second tan 5 over 3, I got here angle 59 degrees. I'm not rounding to the nearest whole number. And vector beta, on the other hand, similarly would be beta is the angle that v makes with the positive x-axis, so y over x, which is 8 over 6. And that will give 53 degrees. So we're going to say that angle theta then must equal 59 minus 53, which makes angle theta equal to 6 degrees. So now we have about everything. We have magnitude of u, which is root 34. We have magnitude of v, which is 10. We have angle theta, which is 6, so cosine of 6. So what we want to do is multiply them all together to see what the dot product in, or the geometric dot product will be. So root 34 times 10 times cosine 6, and I encourage you to use a calculator to see for yourself. We have square root of 34, 10 times bigger, and multiplied by cos of 6. I got 57.99 in my calculator, which I will round it to 58, to the nearest number 58, and I will compare it with the dot product that I obtained from the algebraic dot product. So the answer is the same, and we expect it to be the same. We didn't get exactly 58 in here, it was 57.99, but that is because we had to round the angles in here. So we can see how the geometric dot product is related to the algebraic dot product. Now let's move on to another exercise. And again, always try to attempt the exercises on your own. That's the most enjoyable learning experience, because it's more creative, and it builds confidence in your thinking and trust in your thinking. So let's read the question. We are given the points, sorry for the typo. We have point A, 130, B, and C. Now, even if I wasn't given this information, so if the question states given A and B and C, I would right away understand that these coordinates would represent coordinates of a point, because we're using uppercase letters in here, so be very careful. The idea is we need to find AB dot AC. So let's do this. So we'll say that if I want to find AB dot AC, I'm going to need to know the vector AB. Remember how we find the vector AB. Remember, this is going to be the tail, and this is going to be the head of the vector, which means that when we find the coordinates of AB, we start with x of the head minus x of the tail, y of the head minus y of the tail, and so on. You get the idea. So here we have the x's will be subtracted, the y's, and then the z's. All right, colors actually help us memorize things in a different and a more visual way. So if that helps you, go for it. And I'm going to start with AB. So my focus is on these 2 points, -2 minus 1. Obviously, with practice, it becomes much easier to find the coordinates a lot faster without having to show the work. So obviously, I'm going to show work here. -2 minus 1, that's -3. 1 minus 3 is -2, and 3 minus 0 is 3. Vector AB done. Now we'll do vector BC. For vector BC, now we're looking at these 2 points. So x of C minus x of B, because this time this is the tail and this is the head. So x of C is 5, x of B -2. So 5 minus -2, careful with the signs, it's very easy to mix them up. 2 minus 1, and then 4 minus 3. So that would be 7, 1, 1. So we have the coordinates for each vector. Remember that when you find the coordinates of a vector, so whenever we say, oh, these are the coordinates of the vector, remember that algebraic vectors can be anywhere on the Cartesian plane. So this vector right here, right, is same if I took it here, here, and everywhere. So if we want to identify an algebraic vector, we don't use all the possible positions of this vector on the Cartesian plane. We use only one special position, and that is what we call the position vector. So when we find, or when we say that vector AB has coordinates -3, -2, 3, it means that the tail will be at 0, 0, and these will be the coordinates of the head of it. So by the way, this wasn't exactly vector AB, it was a random vector just for the purpose of illustration. So moving on to finding the dot product, we say AB dot BC equals -3, -2, 3 dot 7, 1, 1. And obviously, again, same drill. We're going to go ahead and multiply the x's together, the y's together, and the z's together and add them. So that would be -3 times 7 plus negative 2 times 1 plus 3 times 1. So that's negative 21 minus 2 plus 3, or negative 20. So negative 20 for the dot product of these two vectors. Now we're going to take a look at these interesting sets of vectors. You recognize these are the unit vectors I, j, and k, which are the unit vectors along the x-axis for I, unit vector of y-axis for j, and unit vector along z-axis k. All unit vectors will have a magnitude of 1 unit, and they will follow the direction of the axis they belong to. So what we're going to do this time is find what the dot product of different combinations of unit vectors would equal. I dot j, remember their magnitudes are 1, so we have 1 times 1, and the angle between I and j is 90, so that will make the dot product ij 0. I dot k, same idea, the angle between them is 90, cos 90 is 0, dot product 0. K and j, 1 times 1, cos 90 is 0, so the answer will be 0. The dot product of the vector with itself would be 1 times 1, that's the magnitude. Cosine, the angle a vector makes with itself, is 0, and cos 0 is 1, which will make the product 1. Same idea with j times j, cos 0, the answer 1, and k dot k will be 1 times 1, cos 0, and then the answer is 1. Now that we have looked at how the dot product works, we're going to take a look at a summary of all the properties of dot product. Remember, we said that very often we study the dot product to study the angle between two vectors, and one of the most common uses is identifying perpendicular vectors. We say two vectors are perpendicular, that means dot product is 0. And we use this statement the other way around. If the dot product is 0, then we can deduce that the vectors are perpendicular. There is something we call magnitudes property that states that the dot product of a vector with itself equals the magnitude of the vector brought to the power of 2. The associative property with a scalar states that if we have a scalar multiplied by a dot product, remember dot product itself is a scalar on its own, then we can multiply this scalar by each vector. You can take turns, so you can say k times u times v, so we can attach k to u and then multiply our dot product by v, or we can dot product u with the multiple kv, where k is again a scalar, any real number. The distributive property states that if we have a vector and we are dot producting it with the sum of two vectors, it works just like in expanding polynomials, so u dot v and then u dot w, so you add. The commutative property states that if you find the dot product of two vectors, it doesn't matter in which order you multiply them, so u dot v and v dot u will give the same answer. Now the next thing we're looking at in this lesson is the unit vector. And for this, we're going to take a look at the next video. Thank you very much for watching, and I hope this all made sense. Bye for now.